All right, so we'll start with the first one. Again, I think at least a good portion of you guys have seen constant coefficient ODEs in high school. So serve as half of a recap, and or if you haven't, it's been a while, and yeah, just as a quick revision of that. Okay. So the first method, the constant coefficient type, we'll talk about both homogeneous and inhomogeneous. Okay, the general theory is very simple. I can sort of summarize it in one slide. So the main form you want to identify, right? So we have second-order differential equation. As a recap, right? Differential equation means an equation with derivatives of y, and you want to solve y of x. You want to find a function that satisfies an equation that has derivatives inside. So second order means it goes up to two derivatives, and now this is the most general form you can have. Of course, these can have x's or y's in here. In general, this can be a function of x and y, right? But if it's just a constant, or I should say, yeah, if all of these are constant, then you are lucky. You have something very simple. It turns out the universe works quite simply. A lot of physical system and in physical applications, whether it's on Earth or in space, turns out a lot of them is actually constant coefficient, which is nice to us. Okay, so once you spot this, the key idea is, oh yeah, and this piece over here is called the inhomogeneous part. Right, so, and hopefully this is all simple recap, right? If f is 0, the ODE is called homogeneous. A lot of the names that mathematicians invent for this subject is a bit baffling. Complementary functions, particular integral, homogeneous. I don't know where they come from. A little bit obscure, but yeah. Okay, so the steps is simple. Mainly two steps. Step one, if you have a homogeneous part, treat it as a homogeneous, solve it first, right? So solve for what's called a complementary function. I'm not going to write it out in full, right? But basically, so for a complementary function, this guy is basically the solution to the homogeneous version. Okay, so treat f of x as 0, solve this first. So even though we give you a problem like that, treat the right-hand side as 0, solve it first, call the solution ycf. It's not the full solution y of x, it's just a complementary part to the full solution. Okay, and then find a particular integral, call it ypi of x, and now you have the full solution. Y of x is the complementary part plus the particular integral part. So it's basically dealing with the right-hand side 0 first, and then, yes?
So what if f of x is constant? Is that going to be infinite?
Ah, good. Very good question, yeah. Very good question. If f of x is constant, how do we deal with it? Is it a homogeneous, or is it inhomogeneous version? Inhomogeneous. Anyone thinks otherwise? It can be both. Well, both could be a correct answer. Why do I say that? It's an excellent question. Yeah. Yes, sir?
Why don't you move the constant to the other side?
Move the constant to the other side. Good. So I force this to be 0, but now I have something like this. Constant, let's say. That still isn't sort of the pure homogeneous form. But you're close, that's the first step. What can I do? Divide through by f, that's sneaky. You've turned that to a 1. Good try, that's the right way of thinking. Is there a clever substitution I can make to make it homogeneous? Sorry? Differentiate the whole thing?
Yes.
You you would make it homogeneous, but you made it into third order. Yeah.
Make a substitution for say u equals y minus f, so that you have it differentiates.
Exactly. Very good. Very good. Yeah. So you explicitly change the whole thing into this. There might be a C, whatever, like that. Okay. Let's assume C is 1 for a moment, right? You can divide everything by C to make that 1. Now, if I put a brackets around this, right, you can call this U if you want. Did I miss a dash? Yeah. Dash. You can call that U, but what's U dash? That's the same as Y dash, right? And similarly, like that. Good. So the whole thing becomes U double dash, U dash, and U. There could be a C, but you can figure out the constants. Yeah. All right. Excellent question. Yeah. Good. This is a general way of dealing with constants on the right-hand side. It's not just for the version 1 for constant coefficient, but for if you have an Euler form or any other form, if you have a constant, this is the sneakiest way to deal with it. Put it to one side and sort of what mathematicians call absorb it into the y and change a new variable. So that one. Yeah, I'll leave that there. Good. You can also treat it as if it's an inhomogeneous part, which I'll talk about the particular, and then find the particular integral for that constant. That is also a valid method, which we'll talk about in a second. Okay. Good. So I'll leave that there. So the main trick, right? This is the main thing you want to remember is try the solution y equals, or mainly the complementary function. So I'm step 1 is the homogeneous part. Try this. A lot of basically integration as a whole exercise of integration is guesswork. So it's really seeing enough typical examples that show up, and you recognize certain methods to solve it. That's why this course is called methods, right? Mathematical methods. And that's why PDEs and ODEs in general is an active area of mathematical research, because you can imagine, you can come up with very obscure ways of differential equation that we don't have analytical methods to solve. So that's what people upstairs are doing a lot of the time. ODEs we're pretty well solved, but PDEs are a very big subject, right? We'll see a little bit of that towards the end of the module, right? Okay, back to here. We'll plug this in. You will get, so double dash each time pulls down the m. So 2 dashes pulls down n squared, em x plus c e equals 0. Remember, we're treating it as a homogeneous version first. Divide everything by this, and now you get an auxiliary equation. Again, baffling choice of names. Okay. There's different names: auxiliary equation, complementary equation, hence complementary function, or characteristic equation. Again, a little bit confusing with eigenvalues, but characteristic equation just means an equation that is sort of characteristic, sort of intrinsic or important to that form of thing. So you might see different names in different textbooks. Okay. All right. And now, usually this has 2 solutions, and either both of them are real. Let me put it on that side. So either both of them is real, so you include both of them. Either they double, you have double roots. What do I do then? You memorize this. There's a reason to that madness, though. We'll see if I get extra time to talk about where that comes from. And finally, if it's complex, so you can write it as the real part plus the imaginary part. Okay, so a real part plus an imaginary part, and the complementary function can take various forms. You can just write it like this. In that case, you have A, e to the m real plus j mi, remembering to write j, and minus that. So you have a real part and an imaginary part, but as you can see, you can, times x, sorry, you can factor out the e to the real part of x, and you're left with e to the plus j mi of x plus e to the minus j mi of x, right? But using the Euler identity, you can change that into sines and cosines, which makes everything, the solution looks more real. But their coefficients will be different. I won't write every step for that, but essentially you have something slightly nicer. And in an exam, well, not only for an exam, but most of physical scenario, this is sort of slightly preferred to have, because you start off with a real question, you want to end up with real solutions like that. Okay. Oh, before I completely erase the methods and knowledge part of the summary, the chapter summary, the exam usually, at least the way last year was done, there's a section of multiple choice and a section of long questions, right? So when you have knowledge parts, don't completely discount that when you're studying. Those are, any parts that are knowledge is a good canvas to ask you in the multiple choice. Right? It can easily ask you, is this ODE, for example, definitions, what constitutes a linear ODE, what constitutes a homogeneous ODE, something like that. It could be a very easy multiple choice question, as well as for methods, it could be asked either in the long question or the multiple choice. For example, if it's an eigenvalue question, obviously it involves methods, but so it can show up in the section B in long questions, but it could easily, if it's a 2 by 2, something that's very simple, and just ask you for eigenvalue, eigenvector, anything that's a method can show up in multiple choice. So by dissecting this, it's really so you get a big picture of the subject, you don't get lost in the forest, but it doesn't mean that don't study that, right? Just so you don't get the wrong impression. Okay. All right, let's